Pretty curves. Now we're going to see that the behavior of a pendulum starts to look like other sorts of waves. The focus, I want to represent harmonic motion in a graphical format and explore waves in nature. A couple definitions before we start. A medium is a material in which the waves move through. Could be a string, could be water, could be air. A wave is harmonic motion that moves through a medium with no actual movement of that medium. Now, there's two kind of subsets of waves. One is a transverse wave, and that means that the vibrations are perpendicular or at right angles to the direction of the wave. An example of a transverse wave is water. Water bobs up and down, but you see the wave move along. Or if you've ever been to a soccer game or a sporting event where people in seats across from the stadium, they stand up at the right time and then they sit down, and then the person to the right of them stands up and sits down, and then the person to the right of them stands up and sits down, that is kind of a transverse wave. Longitudinal waves, on the other hand, are vibrations in which the same direction of the wave. So if the wave is going this way, the objects wiggle this way, and then this way, and then this way. Sound works this way. If you've ever seen a mosh pit, if one guy on one side of the mosh pit shoves the guy next to them, and they shove the guy next to them, and they shove the guy next to them, that's an example of longitudinal waves. A standing wave is harmonic motion that appears not to be moving. You know that it's moving, but the shapes that are generated repeat themselves so frequently that it appears that the wave is standing still. A node. A node is a place on a standing wave that does not move very much. And so, for example, right there would be a node, and right here would be a node, and right here would be a node. An antinode is a place on a standing wave that moves the most, and so up here, this will flip to be down here, and then flip to be up here, and this part of the wave moves the most. We have special names for the topmost antinodes. We call those crests. So here and here. And the bottommost part of the wave we call troughs. So here and here. A wavelength is the distance between either two nodes from here to here, or two antinodes from here to here that correspond to one cycle. And so, for example, if I look from here, this is one cycle. This is where the wave begins to repeat itself. But to be honest, I could look from here to here. That's where the wave repeats itself as well. With nodes, it's a little bit difficult because, look it, I could start here, and I'm like, hey, the wave got back to where it started, but it's going the wrong direction. So I need to keep going. So there. So one wave would exist from here to here. The distance between here and here is called one wavelength. But to be honest, I could use this node and this node as well. That would be one wavelength. Or I could use this node and this node. That would be one wavelength as well. Now, one classic example of harmonic motion is what's called a pendulum. So this is swinging back and forth and back and forth, but unfortunately it happens really fast. But if I slow it down, I can start taking some information like how much time it takes me to get from one place to the next. And so a cycle is simply from one side of the pendulum back to the other side. And we'll see that it takes about 1.4 seconds for my pendulum to do this one complete cycle, back and forth and back and forth. Now what's cool is pendulums will always maintain that period regardless of what kind of weight there is. But the thing is, the amplitude will start to decrease over time. And so I start seeing it begin to not necessarily move as far to the right or not necessarily move as far to the left. This is a characteristic of pendulums. Now, a lot of people say that, oh, it's moving slower. No, it's not. its period is exactly the same. It's still going to be 1.4 regardless of whether this pendulum is swinging really far to the left or really far to the right. What's cool is if I do some video analysis on the pendulum moving through here, you can see that the dots, the points at which the pendulum exists, when they're graphed versus time, begins to make a shape that we've seen before. And this type of curve is called a sine wave. Now you'll notice right here, the pendulum hits 0 amplitude, straight up and down. And then it slows down up here, it stops for a split second, and then it turns around and accelerates towards the center of the Earth again. Now it's not 9.8 because it's not in free fall, but it's a pendulum. What's cool though is depending on where I look at the pendulum, I could get a different shape. If I start by graphing at the pendulum at the very tippy top and not the middle, I can get this hill shape. And you might go, oh, well, that's a different graph. No, actually, it's part of the same graph. We're just graphing different parts of the motion. And then it sweeps back through 0, and then we finish off our cycle by existing in the same place that we started. Well, the thing is, it's going to repeat this motion over and over and over again, and so I get a series of these peaks and valleys and peaks and valleys. And in fact, this graph here shows 7 examples of the pendulum swinging backwards and forwards, backwards and forwards. And I can get either one of the shapes I've seen before by just paying attention to when I start the pendulum and when I stop the pendulum. And finally, resonance is the application of force at the correct time, also known as the period, and the correct direction in order to maintain or increase amplitude. And my example is Mr. Fay pushing Logan on a swing. It's an example of resonance here. I could push Logan, but I do not want to push him at the bottom here. That would be very, very bad. I need to pick when I push. I could push here, or I could push here on the swing as a swing through, or I could push here as well. To be honest, I've seen kids do these things called underdogs in which they continue to push all the way through, getting a lot of amplitude.